Okay, so what I would like to present now is two cases of recent investigation I did with two PhD students, Gaël Burgos and Satish Moria, and other people collaborated to this work. And and so that is the outline of my presentation. The basic idea is what is a plate, what is the role of continents in a plate motion, what is a coupling with mantle convection, and what is the role of mantle plumes. We'll see this point can be addressed by considering Indian continent. And I would like to remind some processes, different processes for seismic anisotropy. Eric did a nice presentation for the seismological part, but we have to relate to the mineralogy and mineral physics, and we will see that there are different interpretations for seismic anisotropy. And finally, I will consider two different examples that we did recently, work for the oceans and at the global scale with Gaël Burgos, and for continent, for the Indian continent. So, okay, so I like this figure because it showed that surprisingly we can relate the small scale, the crystal scale anisotropy to the large scale anisotropy, and it's a long trip from the 10⁻⁹ meter to 1,000 kilometers, and we have different processes at the different scale. Of course, we have strongly anisotropic crystals, but we have aggregate, as discussed Andrea this morning. But at some scale, we have additional process which can be active and which can create apparent anisotropy. It is, for example, here the distribution of cracks or fluid inclusions, and it will, if you have some compressive stress, you will break the symmetry and you will give rise to seismic anisotropy. If you have a layering, fine layering, of course, we will also the equivalent medium, which is seen by seismic waves. Here, lambda W is the seismic wavelength. And of course, what we can see at very large scale, and I only show the first example of inversion of anisotropy at the global scale for 1D model, by the PREM model, we can see that we can start from about 20% of anisotropy, and even in the first uppermost 200 kilometers, we can have an anisotropy up to 10%. So I was always fascinated by the fact that if we go, we have 15 orders of magnitude, and through the 15th order of magnitude, we can still keep seismic anisotropy. So in a sense, it's quite remarkable that we can relate very small scale and very large scale. Okay, but the other point is that you see that I discriminate, I make difference between intrinsic anisotropy, and which is basically lattice preferred orientation, and extrinsic anisotropy, which will come up at some scales. And of course, we have, you see that both will give rise to apparent anisotropy, and the difficulty will be to separate these two kinds of apparent anisotropy, because we know that both are present within the Earth, and so the percentage of intrinsic versus extrinsic anisotropy is not so easy to discriminate. So, to summarize, we have at least three different processes. The most famous one, of course, is lattice preferred orientation, related to olivine, the main constituent, which is very useful because, of course, the fast axis is parallel to the flow direction. So, lattice preferred orientation enables to map convection within the mantle. But as I told you, we have other processes: shape preferred orientation, fine layering, and for example, it was proposed by Kawakatsu et al. To explain the strong radioanisotropy by partial melting in the asthenosphere, and it can give rise to a very strong radial anisotropy. And so you see different processes and influence of mineralogy, of course, water, fluid content, layering, and fluid content, I mean also partial melting, and many applications, of course, because we can use seismic anisotropy to investigate present-day tectonics, geodynamic processes, mantle convection, and also past processes if we consider frozen-in anisotropy. Okay, so the work of the seismologists will be to separate these different kinds of anisotropy in different layers and to provide tentative interpretation. And because we know that the anisotropy is stratified, and that very often it's a real issue, because if you consider SKS splitting, you have only one measurement, and people can build the whole story of the Earth with only one measurement and one azimuth. So when you have a stratification of anisotropy, the interpretation is not so easy. Okay, so I don't want to detail the theory, but basically it's only to show that for surface waves we are calculating the phase velocity by using this complex calculation, but it's not, I don't want to detail, of course. But what is important is that from this kind of calculation we can use an expansion, a Fourier series expansion of phase velocity as a function of the azimuth, which is the angle between north and the wave vector for propagating waves. And we need 4 azimuthal terms. Alpha 0 is named the 0 psi term, but we have 2 psi and 4 psi term. I always remind that if we have to first order 2 psi and 4 psi term, it is because we have to use a 4th order tensor in the calculation. Okay, so if you use this kind of equation, of course, we will be sensitive to 21 elastic moduli. For surface wave, only 13. And I would like to remind that the 0 psi term, which corresponds to the azimuthal average, we have 5 independent parameters, which are A, C, F, Ln. It is the ones which are retrieved by the 1D prime model. And it corresponds to what we call a VTI model, transversely isotropic medium with vertical symmetry axis. From surface wave, of course, we have only 13 parameters, but still a lot of parameters. And so all of them are not easy to invert, and so I only show in red the most important parameters, which are L, which is related to VSV velocity, psi, as mentioned by Eric Debye, the ratio between VSH and VSV. It is also named the radial anisotropy. And azimuthal anisotropy, which is related to the azimuthal variation of SV wave velocity. And by the way, this parameter is also important for explaining SKS splitting. And what we do in seismology is to explain most of our observation by lattice preferred orientation. And the way we do that is very easy. In a sense, from seismic tomography, we have access to 3 different tomographies: S wave velocity, radial anisotropy, and azimuthal anisotropy. And so we have these 3 maps, for example, and of course we can relate these 3 maps to map the flow. You see, for example, if you have upwelling, you will have a slow velocity, but at the same time negative radial anisotropy. When you have downwelling, you will have fast velocities, this subducting slab, for example, and also again negative radial anisotropy, and azimuthal anisotropy will give rise to the horizontal orientation of the flow. So you see, it's very simple interpretation, but we need all these information to explain the seismic anisotropic data. Okay, let me now move to the lithosphere-asthenosphere boundary. And it's interesting because, of course, what is a plate? And if we want to know what is a plate, we have to understand what is the boundary between lithosphere and asthenosphere. And we know from this review paper that we have different definition of the lab. And of course, we have a mechanical definition between the mechanical related to strain rate, where it is almost 0 in the plate, and you have an increase of this strain rate below the lab. We have also another interpretation of the plate. This is a thermal approach by considering the temperature, and so we have the plate where you have only conduction for heat transportation. When we go deeper, we can have more convective processes. On the other hand, it is very similar. From the electromagnetism, if you consider the resistivity or conductivity, you will have also a change in this resistivity profile. And of course, in seismology, we have another approach by considering S-wave velocity, by considering the high velocity lead, where we have a decrease of the velocity below the plate. And from seismic anisotropy, that's an example where we can expect some change in anisotropy when you go from the plate to the asthenosphere. Okay, so we started to investigate the lab from the seismological point of view, and I only remind this old figure. Well, I guess I showed that during the previous workshop 2 or 3 years ago. And there was a strong discrepancy between receiver functions and surface waves. From receiver functions for subducting slabs or at the global scale, they found a lab at about 80 kilometers or 100 kilometers. But from surface waves, usually we find 200, 250 kilometers. And this discrepancy was explained by Yuan and Romanowicz, where they proposed a mid-lithospheric discontinuity between the surface and 200 kilometers. Okay, so now if we look at surface waves, what kind of information can we get from surface waves? And we, of course, surface waves are not well sensitive to discontinuities because they are very smooth sensitivity with depth. And so we tried 2 different approaches by using a Monte Carlo approach. So we assume that we have some discontinuity somewhere, which will be named the lab. And so we'll explore the variation of these depths as well as the velocity in lithosphere and asthenosphere. We can also use a proxy from the depth variation of VSV. You know, is here we have a negative gradient or positive, consider the radius, and so if you calculate the gradient, we assume that the lab is related to the maximum of the gradient. Of course, it's an hypothesis, but in a sense, we will see it's not so bad because, of course, we have no access to the real value of discontinuity, but by this way, we'll have access to the lateral variation. It will be a good approximation for getting lateral variation of the lab. Okay, so that's the basic idea. As I told you, we cannot see discontinuities, but we can see the variation of the gradient of velocities, and so it is what we will call the lab. Of course, we can consider different parameters, and I show here other proxies. We can consider VSV, and so it is by considering the gradient, that is an oceanic profile. The radial anisotropy, in that case, we will put the lab when we have an increase, a maximum of the gradient here. We can consider the azimuthal anisotropy. It's for this oceanic profile, we see it's much more difficult because we have some low for this specific location. We have a minimum of azimuthal anisotropy here, around 50, 60 kilometers, and we can use also the variation in the orientation of azimuthal anisotropy because we can expect that in the upper part we will have a fossil anisotropy, and when we go deeper, an orientation more related to present-day tectonics and plate motion. For continents, it's much more difficult. Well, we can do some work from SV velocity. For the radial anisotropy, it's much more difficult, and we will not try to show any results except for Indian continent, but not at the global scale. So I will presently show the results for the oceans, and we make a compilation, as did many other people, of published data from IPGP, Harvard, Utrecht, Boulder, and so on. And what we do usually, as was previously shown, is to invert for the Rayleigh wave phase velocity and azimuthal anisotropy. We don't see very well azimuthal anisotropy, but it is also inverted. I don't want to detail. Eric and Anna showed a lot of results about that. And in the second step, we use the both approach, the statistical approach, Monte Carlo inversion, and first-order perturbation theory. Okay, so for the Monte Carlo approach, it's only an isotropic inversion, and it is the map here that we find at the global scale, and we see that we can have a lab in continents down to 200 kilometers, and we see perfectly all mid-ocean ridges and quite classical results. And here, that's the associated velocity in the lab. Okay, for the second approach, first-order perturbation theory, we start from these maps, and we calculate the gradient everywhere for velocities and anisotropy, radial and azimuthal anisotropy. And what we find for VSV velocity, so it is the same kind of map as we get previously, so the same distribution of of the lab, except that the depths are larger. For example, for continents now we find depth down to 250 kilometers in many continents, and it is always deeper than for the isotropic inversion. Okay. Yeah. Okay, what was a surprise? And actually, it was when we applied the technique to the radial anisotropy, so we consider the gradient here. And when we calculate the gradient, we can map some kind of discontinuity, not necessarily the lab. And what we find is that except for ridges, it's almost constant. And that was very surprising because we didn't expect, we were expecting to find something similar to what we find for S-wave velocity, but it is not what we find. So you have three different maps: isotropic from Monte Carlo inversion, the anisotropic inversion, so it is the isotropic part of the anisotropic inversion. So the same kind of distribution, but a thicker lithosphere. And finally, this third map about the radial anisotropy, where we find an almost constant distribution of this discontinuity. And here we did very simple. We consider all points everywhere, and we plot the distribution for the oceans. And we use a plate model, so it's not exactly like the square root of the age. It is the temperature is increasing faster for this plate motion. And we show here the statistical approach. Here we show the first order perturbation theory, and we see that for oceans it tends to be slightly deeper. For the azimuthal anisotropy here, we find something which is very similar, but not the accuracy is not so good. If you look at the dispersion of data, it's quite large. And for radial anisotropy, we see that the increase with the age of the seafloor is very limited. And what we find for the Pacific Ocean and at the global scale was also found for the Atlantic Ocean and the Indian Ocean. Here you have SV wave velocity, and here the radial anisotropy, and you see that we have some good agreement with the thickening of, the good correlation between VSV velocity and the isotherm at about 1300 degrees. But for Indian and Atlantic Ocean, we see again that we have some discontinuity, some proxy of a discontinuity around 70, 80 kilometers associated with the radial anisotropy. And it is very similar to what was found previously by Eric de Bail. And it's very, I don't, to be honest, I don't know how to interpret this mid-lithospheric discontinuity. My feeling, okay, Eric showed that some interpretation but what is going on deeper than the mid-ocean ridges. We can also imagine that in the upper 50 kilometers, we have different processes with partial melting below mid-ocean ridges, and maybe it is what we see is radial anisotropy, which is inherited anisotropy at the ridges for different reasons: melting, dehydration, I don't know, small-scale convection. I know that. To be honest, I don't know which one must be preferred, but in any way, it does not mean that we have no radial anisotropy, but only that it is smaller than below. And since we have only access to a very large scale anisotropy, of course, we don't see a strong radial anisotropy in the upper 60-80 kilometers. And when we go deeper, we have a thickening of the lithosphere, which is more the thermal lab, which is different from this one, which might be more petrological lab. And by the way, you see, we might have some inherited plate of about 60-80 kilometers thick. Okay, so that's the first result, and we see that it was not expected to have this kind of intermediate mid-lithospheric strong gradient, and now we can wonder if there is some this kind of result for continents, and I will show you another recent results about continents, following the work by Johan and Romanowicz, where they also found some stratification in the continental plates. Okay, so I will show you some results we got recently with Satish Moria, a student that we share with people in India. And the idea was to use data which are usually inaccessible, Indian seismic data. And the reason why we are interested in India is India is a very specific continent, because it was separated from Gondwana about 65 million years ago. And what is very surprising is that the velocity of the Indian plate was huge, 20 centimeters per year for more than 20 million years. So it's very surprising, because usually we always say that when you have a plate with continent, the plate is very slow, and the issue is, can we explain these very fast velocities when you go from La Réunion to the trip toward the collision with Eurasia? Of course, the Indian continent was ravaged by hotspot, and we have a Deccan volcanic trap here, which is due to the birth probably of a hotspot in La Réunion. And so we can wonder what is the influence of plumes, because different plumes have left some traces in the Indian continent. Of course, we have La Réunion, but there are also Kerguelen and Marion and Crozet, and we have other traps here in northeastern India, Rajmahal traps. And so, you know, what happened is that in the past there was a strong interaction between plumes and continent and Indian continent. Okay, and so there is a debate about Indian lab, which is very similar to what happened for North America. And Prakash Kumar, Kumar is a very popular name in India. So it's a different Kumar. He proposed that Indian continent can move very fast because it is very thin. So Prakash Kumar, in a Nature paper, proposed that the thickness of Indian continent is only 100 kilometers. But there are some other data, for example, xenoliths, showing that the Indian continent might be at least 230 kilometers thick, and other data show that for the Basta Craton, you can have also a very thick continent. And in this more recent paper, Prakash Kumar proposed that you have some flexuring, and so you have a large variability in the thickness of the Indian continent following the collision. Okay, so of course, as I told you, we have to think if we can make some comparison between Indian continent and North America. Okay, so Indian continent is a quite complex continent from the geological point of view. You see, you have at least, it is in the cratons here in a purple color, so you have at least 5 different cratons which can be separated by small rifts. And you have also the Deccan volcanic province, which is due to the huge basaltic province due to the birth of the La Réunion hotspot. So it is 1 million square kilometer and 4 kilometers thick, now slightly smaller of course. But we have all these cratons in different places, and of course we have the collision here with the Himalaya mountain range here in the northern part of India. Okay, for the first time we had access to the seismic networks of India. We have used in this investigation 29 seismic broadband network and over 550 seismic stations, and we use earthquakes of magnitude larger than 5.5, and the distribution of earthquakes is quite nice in around India, and so we could use this all this data, and so we apply our classical technique of tomography for the Indian continent, and we invert for velocity and azimuthal anisotropy, and what we find at shallow depth, for example, is as usual slow velocities corresponding to Tibet, which is due to a very thick crust. And when we go deeper, you can see fast velocities here due to the collision at 150 and 230 kilometers. And we see also some blue spots in different parts of the Indian continent. And we will look in more detail at these different, we'll do different cross sections to investigate if we can see the different cratons of India. An interesting point is the fast velocity here at very large depths. So we find something, it has a limited extent, but you see it's a fast velocity, which is almost north-south object in the center of India. Okay, the results on radial anisotropy were a bit disappointing actually, because what we found is that radial anisotropy is very strong in Tibet, but in most part of the India it is quite small. You know, even okay, we emphasize here some areas where we have some maximum of radial anisotropy, but basically it's always between -2% up to 3%. So to be honest, it's not so well resolved. So radial anisotropy was not so interesting for investigation on the Indian continent. So now let me show you some cross sections in India. So you see here I plotted 6 cross sections. I will detail some of them, but what I want to show you is that what we can see is a large variability in the thickness. You see here we see the lab for the different cratons, and we see that a large variability between different cratons. Some of them are very thin. EDC, I guess it's East Darvar craton. Darvar is around here, and it is very thin, about 120 kilometers. This one is very thick, and we see here that we have very thick root, and in other parts very thick roots, but a large variability in the thickness. And what is interesting is the fact that we have some low velocity channel around 80, between 50 and 100 kilometers, not everywhere, but in many parts, and which might be also associated with the stratifications of continents. Okay, let me show you 2 examples of these cross sections. So here you see, for example, it is a western Darvar craton, which is it is X3 and X4. So it's around here. It is just close to the Deccan volcanic province, and you see that we have this interesting small feature, which is might be due to a low velocity remnant of the hotspot burst. We see also that we have here for central India, which is in the northern part, we have also this low velocity, but not present for the other part of the craton, and we have the subduction here. Here we see difference between eastern Darvar craton and central India. Here you have about 120, you have 200 kilometers. So you see a large variability in the thickness of cratons. Now in the northern part, it is a K3, K4, it is between east and west. And you see now this kind of what we call a keel. It is the Indian keel, which is quite prominent. And we see here the subduction here in Burma, so very visible. But we see that very specific keel with a depth down to 250 kilometers. And so it was also an interesting surprise. And we also looked at yeah, there's something. Anyway, yeah, we also looked at azimuthal anisotropy, and to find if we can find the low velocities in different parts. Yeah, I guess there was I did something wrong. Anyway, and so we can find from the azimuthal anisotropy, we can find the MLD, which is a mid-lithospheric velocity zone, which is also associated with VSV variation, and we plot the gradient to extract this discontinuity, and also the lab at larger depths. In that case, it's about at 150 kilometers. And we did that systematically for the different cratons, and I only show the results for azimuthal anisotropy, and we see that we have some change, and we can associate this change in azimuthal anisotropy to the existence or non-existence of this mid-lithospheric boundary, which is a mid-lithospheric low velocity zone. Okay, so you see a lot of variability in Indian continent. And finally, probably one of the most interesting results is the existence of the keel, because it is found, you know, it is oriented almost north-south, and it is in the middle of the Indian continent, and it is associated with some, well, we don't yet understand all the azimuthal distribution of of the velocity of the azimuthal anisotropy, but you see that it is a quite prominent feature. And we can wonder what is its role in the dynamic of the continent. You know, we make the comparison with the keel of a boat. When you have a boat, when you have the keel will have a strong influence on the orientation of the motion of the boat. And we can wonder if this keel didn't play a strong role in the motion from the south to the north, and maybe it will not avoid to have strong velocity, even though its thickness is 230 kilometers. So we would like to work on the geodynamic interpretation of this keel and to understand what is its role. And we suspect that it might be due to the interaction between the plume, Lagrangian plume, and the Indian continent 65 million years ago. Okay, so I will. Oh, what happened?
It's time for question anyway. So, yeah, you can put back. Thank you, Jean-Paul, for this talk.
Conclusion.
Yeah, just your conclusion.
Yeah.
Otherwise, we won't have time for questions.
It's a big file, maybe that's the reason why.
Yeah. But it's nice to see the consistency with the talk from Eric just before. It was really nice to see. What's your conclusion?
Yeah, so the conclusion it is what I showed. We have, for the Indian... No, it doesn't work.
Okay, yeah.
Ah, yes, it's okay. Yeah, so the basic idea is that we have large variabilities in craton thicknesses. We have this low velocity zone in the middle of the continent. I guess the interesting point is the Indian keel, and we don't understand this geodynamic role. And finally, okay, that's the last one. And I show here the Indian keel. We start to do some 3D plot, not yet perfect. This is the south, that is the north, but you see this Indian keel, which is quite visible here. Okay, thank you.
Thank you.